And what I'm going to do today is a variation of what I did then. So just in case you like what I do today, you might want to come along to the museum next year. I've got handouts here which summarize what I'll do today. So I've got lots of tricks today that you can take home and try on your kids. But there's also an announcement for what's going to happen next year. So today, it's not just here for decoration, the magic and the miracles, it's really all about magic and miracles. So, I mean, you've all heard of people levitating, Jesus feeding the 5,000, vanishing into thin air. And today I want to tell you how to accomplish all these things with mathematics. Right. You can do it, I can do it. So, well, there's a bit of bad news here. My sorcerer's apprentice, he's vanished already. My sorcerer's apprentice has got a runny nose and couldn't come. Usually I have him here, and he works the crowd for me, right? And whenever that happens, I don't have any problems with anything. But since he's missing today, we have to do a little bit of a warm-up exercise. Not that anybody really has to warm up here. I mean, in fact, I would have looked up a cold spell if I had known that La Trobe doesn't save on air conditioning. All right, so we have to do a warm-up exercise, and first the warm-up exercise for you. So we're all going to raise our hands. Very good. Yeah, you can all do that. Fantastic. All right, now we're going to clasp our hands like this. All right, you can all do that? Yep. Now, this is going to be very good. All right, now we're going to turn things around like this. Now we've got 2 index fingers. So index fingers. So what we're going to do now is touch our nose. Back to our legs. Now we're all going to play Houdini. You're going to unclasp your hands. Well, this is just to kind of figure out sort of speed. You clasp your hands over. Very easy, right? Okay, I don't do this for warm-up, I just do this to figure out what I can get away with, okay? Okay, so here's my warm-up, this is sum, right? 340, 437, 47,813, and that sums up to, I claim, I'm just going to do it, okay? I need a magic wand for this. The magic wand is not long enough. Right. Alright, I'm going to just wave my magic wand and make it into the right thing, okay? I'm not impressed, alright? Okay, so I have to work harder. Okay, so now the real thing, buried alive, right? You've all heard about this trick? So basically it works like this. You need a volunteer. Right? You need a volunteer. Who wants to volunteer? You don't want to volunteer. Okay, so you dig a hole in the ground, right? You purchase a coffin, you put the volunteer inside, right? You put the volunteer inside the coffin, inside the hole, and fill it up with dirt. Then you wait 32 days, okay? And you watch. You have a little campfire. And then you open it up, right? Now, if you find a dead guy in the coffin, then it's not a magic trick, okay? However, if he's still alive, right, everybody's impressed, right? And it counts as a miracle. And I mean, people perform this trick. And the first thing I want to tell you today is how this trick is performed, right? With mathematics. Now it's a bit hard to do this, I can't dig a hole here. So what I'm going to do is what many mathematicians do when they're faced with something difficult, they make it a bit simpler. So I'm going to show you how this trick is performed in 2 dimensions, right, in flatland. Okay, here's how that looks like. So that's the setup. Right? Flatland is just a play. Flatland is just a play, right? And there's people living in flatland. Here we've got our volunteer. His name is Houdini. There's a couple of features here. So this volunteer, he can only move around in the plane, right? So the plane only has 2 dimensions. So they can kind of hop around here. You can hop around. They can kind of rotate like this, but they can't really do anything else, right? And you see, I mean, like the digestion system is a bit different from ours. If it went through here, the thing would actually fall into two pieces, right? So there's you don't want it to happen. So, I mean, basically you have to regurgitate all food. There's all kinds of other really interesting features here, but we don't really want to go into this. We want to bury this guy alive, right? And we want to do the buried alive trick. All right. Okay, we also need an audience. So there's the audience. So all people in Flatland are born facing left, right? So basically you can only walk like this. You're going to hop like this, right? That's what you can do. But the other thing you can do is you can kind of rotate on the spot, right? So if you want to face somebody, you actually have to stand on your head. So that's what all these people are doing, right? So there's an explanation for everything. All right, now let's open up the coffin, put the guy inside, close the coffin, fill with dirt, and now air is running out. Right? This happens. Now, there's no applause, right? There's no applause, because these guys don't see anything. But all of a sudden, this happens. Appears in, mid-plane, right? So, how does this work? How do you possibly perform this trick? So I'll do it for you in slow motion. I mean, usually you would wait for 32 days, of course, right? So you would just be somewhere drinking coffee, right? Where's Houdini, right? So in this stage, you actually find him out in three-dimensional space. Right? So he starts out here in the plane, but he's the only one who's figured out that there's a third dimension that extends his plane. Right? And what he does is, he just enters the three-dimensional space, and for everybody else, he's gone, right? He's gone. He's out here drinking his coffee, right? Drinking his coffee, and then after 32 days, well, he just appears in the air. That's how you perform. Buried alive trick in two dimensions. The same trick you can do all kinds of other stuff. So, for example, you can walk through walls, right? Same principle, right? So there's the wall here. There's Houdini, approaches the wall, takes off into the third dimension, moves over here in the third dimension, and reappears on the other side. For everybody else here, who are restricted to the second dimension, this appears like a miracle. For Houdini, that's not a problem whatsoever, right? As soon as he's figured out how to operate in three-dimensional space, he can do all these tricks. What about levitating? So I'm his friend in the third dimension. What I can do is, I can just poke my finger here into the plane. For people here in the plane, what would that appear like? That would appear like a point appearing in mid-air, and a solid point. That point doesn't move, right? That point doesn't move. So what Houdini can do is, he can just kind of hang himself on this point. For everybody else, this seems like he's levitating, right? He's not. I'm holding him, right? I'm holding like this, right? I might stop his heart like this, but I can hold him, right? In fact, I can do closed heart operations on Houdini. I can operate. I mean, everybody else here in the second dimension, they don't see the innards of this person. I can see every point here, so I can operate. I can do transfusions, right? From one to the other. I can go from here to there, no incision. It's a miracle surgery. So you can do all kinds of miracles. You can do it in two places at the same time. How does that work? Well, let's say this is the world that he lives in, okay? This is the world he lives in. Everybody else moves around here. Say we've got 2 points here that are far apart. Those 2 points are far apart, right? Now everybody in here thinks, well, it takes forever to get from here to there. However, you don't know how this piece of paper is embedded in the surrounding space. So it could be embedded like this, right? So all of a sudden these 2 points are very close together. So if Houdini knows how this piece of paper is embedded in three-dimensional space, he can just jump from one point to the other through the space, whereas everybody else has to move like this, right? In this way, he can be in 2 places at the same time. Another thing he can perform is, he can turn himself into his mirror image, right? So everybody else can just move around like this, turn upside down, do all kinds of things. If you can actually enter three-dimensional space, you can turn yourself into your mirror image, right? And you'll be the only one who faces. Fantastic, right? That's actually not such a good thing. Right? If we could turn ourselves into a mirror image, say I have an apple, I've got an apple, I'm prepared. I turn this apple into a mirror image, and I try to eat this, it's indigestible. The mirror image of this apple is indigestible. So you can actually die, and also the air and everything else. So turning yourself into your mirror image might not be such a good idea. Alright, so all kinds of things that you can do So for example, turn yourself into a mirror image. Right. Now there's one trick among all these that you can actually perform without having to go into the third dimension. And that is turning yourself into a mirror image. Well, under certain circumstances. Sometimes you just have to know where to go. Okay? So here we go. So you only need this. What is this? So everybody's seen this? This is a Möbius strip, right? Möbius strip. You just take a strip of paper, twist it once, you don't have to do this. And, well, this is a special kind of flat ledge. If I make Houdini appear here, in the starting position, and just make him walk around this Möbius strip once, okay, and he finishes down there, now he rotates on the spot, and he's turned himself into his mirror image. So walking on the Möbius strip, turn yourself into your mirror image. So you can do this, if you know where to go. Alright, now, of course, you're not interested in how all this is done in two-dimensional space. You want to know how to do this, you know, in your classroom. You want to vanish into thin air, for example. That might happen quite often, right? Or you might want to just make somebody disappear, right? This person there, huh? Want to disappear for good, right? So the only thing you have to figure out is where is this elusive fourth dimension that extends our three-dimensional space. Exactly the same kind of principle. In fact, kind of scientists don't know whether there's a fourth dimension, a spatial dimension that extends our third dimension, but they also haven't disproved it. Now, people like me, we know how to do this, right? And we can do all these kind of things. And we do it exactly like how Houdini does it, right? So if you kind of understand what how Houdini does when he performs his miracles, that's how I perform my miracles, right? So I can vanish in mid-air, levitate my assistants, and knotting these things without cutting them, unlinking things. I can turn myself into my mirror image. And just to give you an idea what it would be like to be persecuted by a monster that can enter the fourth dimension, here I've got a little bit of a movie clip from probably the worst horror movie ever produced, which is called Shriekers. Anybody seen that movie, Shriekers? You haven't missed anything. All right, so there's the scene. We don't have audio. Wait. We have one. Maybe it works. This is not very good, but I can't get it higher on this one. Sorry. All right. Okay, now, of course, I mean, you're not really interested in math that I'm going to talk about today, right? You're just here for the magic. Okay, so you're ready for some really bad magic? Okay. Let's see what I'm ready to. I just have to figure out whether we can actually up the volume on this thing a little bit. I have to do this by hitting the screen 500 times. Uh-oh. Sorry. Martin, can you just hit the screen 500 times for me, please? This is really chaotic. I think I have to hit this lots of times.
Okay. I'll keep you.
Or maybe we can do this. No, we can't do anything. Sorry, it's going to take 5 minutes here on this computer.
I'll do it.
You do it? Okay. Right. Okay, so the first trick I'm going to do is I'm going to make, I need a special hat for this. For every trick I've got a hat. Are we getting there?
Yep.
Getting there?
Slowly.
Slowly. Oh, and I just switched off the thing. This is another trick with this computer. If you hold on to it so that it doesn't move, you actually switch off the screen. Okay, the special hat, it's my proudly Irish hat. Alright? Just imagine you face a classroom full of people, right? And you really want them gone, right? Okay, here's the trick. Here's the trick how you make them all disappear, okay? Ready? 1, 2. They're gone. Now you can't make them reappear, otherwise, you know, you just leave it like this. Face the other way. Right. They laughed, they're impressed. Fantastic. Okay, next trick. I'm actually not a magician, I'm a juggler. Right? So I'm a juggler, and so that means I can actually tell you these secrets. I mean, real magicians, they have to take the oath, right? And they get crucified if they, divulge secrets. But since I'm just a juggler, I can actually do all these things and do whatever I like. Okay, so here is a juggler magic trick. So that's 3 balls, right? 3 balls. Now this is 4 balls. This is 5 balls. Thank you very much. Now, I've got another one. We want to, actually, I've got an assistant for this one. I did this in the museum, but nobody could see anything. So I've got an assistant for this one here, and the assistant is David Copperfield. Ever heard of him? Second-grade magician who was doing it. So, what he's doing is something impossible. He's got 2 of those, basically, rings, linked, right? Linked. He uses rubber bands. Maybe I have some rubber bands somewhere. Maybe not. So what he does is he creates 2 linked rings. How? Well, you put a rubber band around here, and you put a rubber band around here, and you have them linked. Right? And you can stretch it like this, what he does. And then he magically makes them come apart. And you can do this if you can move into the 3rd dimension, no problem. It's just the same as going through a wall. So here's how he does it. Right, so you have to move fast, right? So this thing into the 4th dimension is one. All right, now I want to levitate something. This is actually hard work. It's hard work. If you don't have anybody helping you from the 3rd dimension. So what do I need for this? I need a special. Let's just see how this works. Listening to music. I need a trombone. Okay, so that's all you can do with the 4th dimension, all right? All you can do with the 4th dimension. There's other things you can do with mathematics. Okay, what have we got here? The feeding of the 5,000. Anybody heard about this? So basically the story goes like this. Jesus and his disciples are tramping around in the desert, right? And they pitch a tent somewhere, and all of a sudden they're surrounded by 5,000 people, right? Hungry people looking at them, right? They're the only people who have any provisions. They have got a couple of loaves of bread and some fish, right? Definitely not enough for those hungry people, so they get very worried. But Jesus says, don't worry, right? Don't worry. Do something miraculous. And he does something miraculous, and everybody gets fed, and there's stuff left over. And I want to show you how to do this with mathematics. And this is actually a trick that you can do with your kids. Okay? So here we go. We're going to feed them with chocolate. The kids want chocolate. They don't want fish, right? Okay, so first we need some magical numbers. You shout out when you recognize the sequence here. We've got 1. All right, you all got it, right? Fibonacci sequence, right? Fibonacci sequence. 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Right? So magic. Magic appears everywhere in nature. You've all seen it. You teach all this stuff, right? You look at spirals here. How many spirals go this way? How many spirals go that way? You find 21 and 34. 2 in the sequence. On the pineapple, there's also different kind of spirals here. So you just count how many of those spirals. 1, 2, 3, and so on. So you get 5, then you get 8. So 3 consecutive ones. And all kinds of other places you find the Fibonacci sequence. But today, we're going to use it for feeding the 5,000 with chocolate. All right. So we're just going to choose one number. You can choose any number here. So we'll choose 8. We'll choose 8, and we make up a bar of chocolate that has dimensions 8 times 8. So there we go. And then we cut it up according to the previous two Fibonacci numbers, 3 and 5. Oops. There we go. So you make a horizontal cut here at 3, and then the rest is 5. And then you go over here, 1, 2, 3, 4, 5, okay? And over here you go 1, 2, 3, and you make another cut that gives you 4 pieces. So the piece of chocolate here has 4 pieces. You reassemble it into a rectangular piece of chocolate. And now comes the trick. To figure out what the area is. The area of the square is 8 times 8 is 4. Okay. The area of the rectangle is 30 times 5 is 5. Okay. So you gained some chocolate here. Okay, so that's good, right? What you do now is you take this one piece of chocolate and just melt the whole thing, turn it into a square again, do this 5,000 times, right? 5,000 extra pieces of chocolate. And that's how Jesus did it. Now you can get it wrong, right? So you may have chosen 13 instead. Right? So do the same kind of thing to 13. Same kind of principle. Start with 13 times 13 square. Cut it up according to the previous two numbers, 5 and 8, right? Reassemble. Figure out what the areas are. 169, 168. Right, so you do this, nobody's impressed, right? And in fact, that kind of continues, right? So if you choose the 8, you gain. If you choose the 13, you lose. You gain, you lose, you gain, you lose. Keep on going. So it works for all of the Fibonacci numbers. So it's really, really quite neat. So you can definitely do this with your,
When you buy the chocolate, it's usually rectangular anyway, so you can start with rectangular.
True. True. So I start with this one, right? Okay, of course it's a dirty trick, right? Dirty trick. So when you actually with really close look, you find that these things don't really line up very properly. So there's actually a little stretched something in between if you align things perfectly, and that's where the missing one piece is gone. And so everybody's disappointed now, but the kids won't notice, right? If you don't tell them, they won't know. Now, if you don't like this kind of puzzle here, this kind of magic trick, Bill here is going to talk about this and other really fantastic things. So he even has diagrams on these things, and they reassemble into different things and form a story and all kinds of other things. And that's going to happen tomorrow at 10:45. Really magical puzzles tomorrow at 10:45. Now I'm just going to tell you something about like really deep mathematics, where I can't really show you much. It's the Banach-Tarski paradox. This is something that I want you to know. Anybody heard about the Banach-Tarski paradox? All right, Banach-Tarski paradox. So there's these two mathematicians, long dead, and they came up with something amazing. So what they proved is that if you have a solid ball, like this one here, solid ball, right? Solid ball, you can dissect this thing into 5 pieces, 5 pieces, right? 5 pieces, 1, 2, 3, 4, 5, right? And move them around, and reassemble those 5 pieces into 2 solid spheres. Right? So you start with 1, you dissect it into 5 pieces, right? And you can reassemble those into 2 solid spheres. Right? So you don't deform anything here, they're really rigid, right? Rigid 1, rigid 2, rigid 3, rigid 2. You can move them around in space, you can put them together again, and you get 2 solid things. Now that sounds completely stupid, right? When you think about it, there's 5 pieces, they each have a volume, right? They each have a volume. Well, if you start out with something like this, it's like volume 1. So these two have volume 1. Obviously, when you put them together, you can't have volume 2, right? Can't work. But the trick here is, those things may not have volume, right? So these are really, really strange kind of sets. So if you try to construct those using a cleaver, you would never get there, right? You would not be able to construct those 5 pieces with a chopping board and cleaver, but you can do it mathematically. And people actually got very upset about this, so they thought this was an abomination, it had to be, you have to get rid of this, and even wanted to forbid people to teach this at university level at some point. But I mean, it's still around. In fact, people proved that if you go and get rid of this, right, if you don't allow this, then you get rid of a lot of mathematics, of really, really good mathematics. And mathematics is built on axioms, right? So you've got these fundamental facts that everybody kind of accepts. And if you get rid of the paradox, you get rid of one of those fundamental facts. It's called the axiom of choice. It basically says, if you've got a couple of sets, a set of sets, then you can make another set by just choosing an element from each of them and assembling something to this. So it's very kind of innocent kind of looking thing, but if you allow that, you also have a lot of others. So you kind of go full circle here, like with the Jesus story. You either believe it or you don't. You have to take this on faith, right? With mathematics, it all seems like there's no discussion about whether things are right or wrong. But if you go back to the foundations, there's also a lot of faith involved, right? You either accept these axioms as something self-evident or you don't. Right? So faith involved in mathematics, faith involved in real miracles. Okay, so these were all real miracles, but real miracles can't be explained by, physics. Now I'm going to talk a little bit about magic tricks. Right? So all this was real, right? Even this was real, right? This is something that was performed by David Copperfield. Years back, he had this TV show every year, and what he would do is he would have one trick where he would get the TV audience involved, right? And I'm going to show you one of those things, and basically all of those tricks are based on some mathematical principle. And this is one of the nicest ones. It's in the movie about the Orient Express. So at some point he makes a whole carriage of the Orient Express disappear. But just before he does that, he has this clip where somebody murders somebody else, and he plays a detective and finds it. So basically, just watch the clip. He's going to explain everything. And eventually, you actually have to follow what he says, right? He kind of refers to the TV screen, but you can just do it here on the screen. And I would advise you to just kind of point at things, kind of close one eye and kind of move around like this and follow whatever he has to say.
Tonight, you'll be the murderer.
And I'm the detective. We're going to have some fun and do something totally different. Here's the idea. Tonight, you, the murderer, are going to put your finger on the car and move around the train. And I'm going to find you. And the amazing thing is, even though you're at home and I'm here, I'll know exactly where you are. And the car that I find you will be the train car that I attempt to vanish tonight. Here are the rules. In a moment, I'm going to ask you to choose a car to start. Then I'll ask you to move, say, 4 times. For example, if you're going to choose male, you could count up or down, side to side, frontwards, or backwards, on any adjoining car, like this. 1, 2, 3, 4. Or 1, 2, 3, 4. There are infinite possibilities, but never move diagonally. This is your last chance to participate. So come real close to your TV, so you're able to touch the screen. Right now, go ahead and select one of the cars to start by placing your finger on the screen. It's your choice. Touch a car now. Good. Keep your finger on the screen. I'm going to make it even harder for you to find by adding more cars. Get ready to move to 4 other cars. Remember, never move diagonally. Never skip over cars. Just up or down or side to side with 4 other cars. Move as I count. Ready? 1, 2, 3, 4. When you finish, leave your finger on the last car you touched. Now I know that you're not in a stacked car, so I'll take it away. When a car has been removed, you may not move onto that space, but you still have 8 other cars which to move. With your finger on the last car you touched, stand by and move your finger up or down or side to side to 5 other cars. It's your choice. Move as I count. Ready? 1, 2, 3, 4, 5. Okay, I can tell you're not in the club car, so I'll remove it. Now move 2 more times. Ready? 1, 2. Good. I can see you're not in the mail car, so I'll get rid of the mail car. Move 3 times. Ready? 1, 2, 3. Okay, I know you're not in the baggage car or the caboose. There are only 4 cars left. Now move 3 more times. Ready? 1, 2, 3. A few seconds ago, many of you were in the shower, but you're not there now, so I'll take it away. Remember, you have a free choice every step of the way. Stand by to move one. Ready? Move. And keep your finger there. Remember, you started where you want and you move where you want. But believe it or not, even though you're at home and I'm here, I know exactly where you are. You, the learner, are not in the engine, and not in the bar. You're in the dining room. And that's the train car. Oh, that's the advantage too.
Right, good. So somehow people are more impressed when this guy does it. I've never been able to figure out why that is. All right. So I mean, you may be wondering about the bad quality of this clip. You can actually not buy these things. So this is actually a pirate copy. I think it's off a TV program in Kuala Lumpur. Don't ask me how I got it, but you went to great lengths to procure these kind of things. All right. So now, I'm going to ask you this question once. Who wants to know how this works? If you don't want to know it, I'm not going to tell you, right? So you have to raise your hands now if you want to know how it works. I think the majority here, there's some people who don't want to know. All right, I'm going to tell you. All right, so this is the setup here. This is the setup. So you've got 9 cars. And to start with, you have to choose one of these 4 cars. This one, that one, that one, or that one. Right? Now, I'm just going to color these things a little bit. Right? So they've got the 4 blue cars. You have to choose one of them. Then there's the 4 red cars. Now, there's really just one very simple observation that you have to make here. Every time you move, you change colors. Right? You move, you change colors. You move to change colors. Doesn't matter where you move, you change colors. So what does it mean if he says, make 4 moves, and you start on a blue card? This is 1, change, 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 change. Right? So he knows after 4 moves, you're all on blue cards. Doesn't matter what you do, you're on a blue card. Right? That means you get rid of some red card. Right? It's fantastic. Okay, then he makes 5 moves. Right? 5 moves means you change colors. So basically, odd number of moves means you change colors. Even number of moves means you stay on the same color. And that goes all the way through. And basically, on every step, he has one color where he can just choose freely and just get rid of these cards. So in this case, we've changed colors now. So we are on red. So he can get rid of one of the blue cards, and he chooses the club card. Right? Now he does 2 moves, so he stays on the same color, he stays on red. You can get rid of 1 blue card, and it just keeps on going like this. And it whittles down to just those 2. And basically he knows that you're either in this one or in that one, and he asks you to make 1 more move, and that takes you all into the diner, and that's it. And if you ever get hold of his TV performances, there's always one where he asks the audience to participate, and it's always based on a really, really nice, neat mathematical principle. So there's one for you. Okay. Just as a kind of transition to the next thing, I'm going to teach you how to square the circle, all right? You all know it's impossible. What does it involve? You have a circle, right? And you want to turn it into a square of exactly the same area, okay? Now what is exactly the same problem is circling the square, right? Circling the square means turning a square into a circle of exactly the same area. Okay, I'm going to do it for you. I'm circling the square. Well, the circle doesn't really have the same area, so we have to try something else. So just follow this. I'm going to dissect it. Right, dissect it. And now I'm going to go. Right? Circle and square are the same area. No doubt about it. All right. Of course. I mean, the real circling of the square involves something else. I mean, it involves ruler and compass constructions, right? And it has been proved that it's absolutely impossible, right? So if you have start with a circle, right, and you go wild with ruler and compass, and you want to square up the same area, you cannot do it, right? You cannot do it. But in fact, it's possible. It's possible. That has been proved that if you have a circle, you can dissect that into finitely many pieces and reassemble those finitely many pieces into a square. So they've proved that it's possible with less than 10,000 pieces. So you can cut up the square, and you can cut up the square with a cleaver, right? 10,000 pieces. That's not one of those really, really bizarre things with the Badach-Parsky thing. This you can do with a cleaver, cut it up, reassemble it. Quite amazing. Okay, so David Copperfield also has a program about the Bermuda Triangle. Has anybody seen that? No? Okay. Well, has anybody here had a relative who went missing in the Bermuda Triangle? No? All right. All right. So you're going to be the relatives now who everybody talks about who went missing in the Bermuda Triangle, all right? So it gives people something to talk about, and maybe your kids, they will be happy because the teacher disappeared, right? All right. So people have talked about this a lot. I mean, we've tried to find reasons for why so many ships, planes, people go missing in the Bermuda Triangle, right? So the Bermuda Triangle is somewhere here. So Miami, Puerto Rico, Bermuda, right? Somewhere in here, lots of people get lost. But what has never been mentioned in all those discussions is that this triangle here is really very close to an equilateral triangle. Okay, so I'm going to send you all to the Bermuda Triangle now, and for that you need your paper strip. Okay, so first watch what I do. First watch what I do, and then we're going to do it together, okay? Alright, so first what I'm going to do is just crease this piece of paper, and I'm going to highlight it. So don't do anything yet. It's very important that you just watch what I'm doing. So I'm putting a first crease in, okay? Then I'm going to refer to creases, the top edge and the bottom edge of the strip of paper. What I'm going to do now is align this top here with the crease. For that, I just fold it down like this. So now the top edge is aligned with the first crease. And what that gives you is the second crease. Right? Okay? And then you do exactly the same with the bottom crease, with the bottom edge. You just fold it up and align it with the second crease. And that gives you a third crease. And then you just keep on going, and what you get this way is, a zigzag line. Now you can choose any crease you want. You can make it really, really horrible. You can make it really horrible to begin with, right? And then I want you to do this, as long as you want, and have a look at those triangles that you get here on the way. So let's do it all together, right? I'm just going to repeat what I said. It's really quite straightforward. So, put in a really, really horrible crease. This is horrible, right? This goes all the way